Okay, previously we mentioned about how the green area, the green layer and the orange layer can be formed on the top of the ion surface. Okay, so there are two products under oxidation process. This is FeOH2, ferrous hydroxide, and again I label the wrong name there because ferrous hydroxide, FeOH2, the two, if you see the two FeOH2, this one is the green color. Then if you see the FeOH3 is the orange color. Okay, so there's I purposely put them in their color so that you can differentiate. Okay, so this one is ferric hydroxide. This is ferrous hydroxide. Okay, and this one, if you see 2, is iron 2, iron 2 hydroxide. This one, if you see 3, means this one is ion 3 hydroxide. Okay, so these are their color. Now, previously, when we mentioned about the before our previous class, we mentioned that the FeOH3, the ferric hydroxide of ion 3 hydroxide, is in neutral pH, and there will be three layer. There will be 3 layers on the surface. So another layer is called Fe3O4, which is a ferrous ferrite, ferrous ferrite, which is in black color. So this one, so on the corrosion surface on the metals, we have three layers. Okay, we have 3 layers, and in the middle is a black color one. It's a black color. This one, Fe3O4, and combined with the dot N means it can be a lots of water molecule around this element. Okay, so if you see a dot NH2O, then hydrous ferrite. Then you add in one adjective in front of the element, hydrous. Right, means come with the water. Okay, and previous class actually I missed out one PowerPoint slides. So I want to show you the color of the this one, the Fe3O4, the color. Okay, so I did show you the FeOH2, FeOH3 color, and I want to show you the black color. So it is this color. So again, this one they use acid to form the thing. So let's watch this.
Hello students, today we are going to make ferrofluids. To make ferrofluids, we have to synthesize Fe3O4 nanoparticles. In order to make Fe3O4 nanoparticles, we need 2 iron sources. One is Fe2+ and one is Fe3+. So we have here 2 molar FeSO4 solution, 1 molar FeCl3 solution, and to precipitate out the iron oxide, we have ammonium hydroxide. So to begin with, we will take FeCl3 solution. Then we are going to mix the Fe2 sources. And we have already filled in the ammonium hydroxide in the burette, and we will add dropwise. So what you will see that iron oxide will start to form as a black precipitate, and we have to do this slowly in order to maintain the particle size. So as you can see, the color has already started to change. and black precipitate has already formed. We'll continue the stirring for some time. After that, we'll filter out the nanoparticles, iron oxide nanoparticles, and then we'll see the effect of magnet on these. We can still So we filtered out the iron oxide nanoparticles, dried the sample, and then we mix it with oil. And now you can see we have a magnet here, and these particles are magnetic, and they can be used for various applications where ferrofluids are used.
Okay, so from the video, again, I show you that ferric oxide have two characteristics. One is non-metal, one is metal. The one that I show you in this video is have a metallic magnet, sorry, non-magnet and magnetic. So the one that you see in this video at the end, I think last 10 seconds or 20 seconds, the researcher used the magnet at the bottom of the container, and then you move around. Okay, today we look at pH, potential pH diagram. All right, potential pH diagram. So a name for EPH, potential or potential pH diagram. We mentioned this name before, right? Froberg's diagram. What does this diagram will tell you? It tells you about thermodynamic data and the behavior of metal and their species, the chemical species in that environment. Okay, I'll give you an example. Okay, so you can see the detail in about the EPH diagram in Appendix D. So I expect you go and download this Appendix D and read about it. Okay, read about it. So this appendix, inside this Appendix D, there are lots of things to read. I think it's about 40 pages, but only one section, talk about maybe one or two, I think 3 pages talk about the Froberg's diagram, but the rest you can read as your for your own information. Okay, but to understand what is a Froberg's diagram, it's better you read the whole document so that you know what is the technical term for some of the process, one of the reaction. So I have uploaded Appendix D. If not, then later you let me know. Okay. Okay. Again, there will be one additional document that you need to read today as a homework before next class. You go and read Appendix D. Okay. Let's look at EPH diagram or Froberg's diagram. So generally on the potential pH diagram, this one is already simplified. Already simplified. It's not this simple. Right? So on the Froberg's or EPH or potential pH diagram, on the left-hand side you will see voltage versus pH. pH is the acidity or acidity of the solution, right? The more pH, the more on to the left will be more acidic, the more to the right will be more alkaline. So if you have the potential versus pH diagram, there will be an area, we call it mode definition. So inside the EPH diagram, inside the diagram you see a lot of information there. So there will be particular section that inside the diagram you will see the mode of the definition. For example, you see the FeOH2, FeOH3, and sometimes you see FeO in the diagram. Okay. Next will be on the same diagram. Sometimes you'll see environment definition inside there. All right. So one is the mode information inside the diagram. Another one is environment definition. Environment definition means you refer to pH. So either it's more alkalic or more acidic or more alkalic for the environment. Then some process will happen. Mode means some process or the product that appeared in that particular pH, and potential also. Okay, so generally when you look at potential pH diagram, there are two idea or two information you can extract here. One is their mode, means their status or their state or their phase, because you mix with different, you know that we have gone through, we have covered lots of equation. So during different pH, they will react differently. So information, the first information on the pH, potential pH diagram will be the mode. Second one will be the environment that contribute to the mode. Okay, so these are two main information that you can extract. Okay, again, the detailed information you can read from the appendix D that I show you just now. Okay, so this one and environment. So this one I will in our next chapter or maybe next section or next week, I will give you more information about EPH diagram when we talk about kinetic, maybe kinetic properties of corrosion. Then there was some calculation or there's some drawing on the sketching on the EPH or construction of the EPH diagram or potential pH diagram. Okay, then somebody, one researcher, let me try to read his name. Staley, right? Or right. So you can read lah, right? This researcher, he proposed that actually we can combine these two information on the same graph. Okay, on the same graph. So information, the overlapping of this area will help you to identify the mode and the environment together. Okay. Yeah. So this graph is proposed by this researcher that you can actually overlapping these two information together on the same graph. Because on the potential pH diagram, sometimes you don't see this one, sometimes you don't see this one, but and also sometimes you will see both of them overlapping together. It's like you are plotting different graphs overlapping each other. Okay, so it depends on how detailed you want to observe or what are the experiment you are conducting. So yeah, so don't be surprised. Sometimes why there's no environment information? Why sometimes the mode is missing and focusing on environment, and sometimes you see there's a superposition or overlapping of these two data inside one graph. Okay. Okay, so I put this one on one side. So today we will learn new terms. It's called EPH diagram. And the more detail again, you need to read appendix D for it lah. Okay. So this diagram will tell you the thermodynamic stability about the corrosion process. Yeah. So the rest is you just read from the axis. For example, potential. At this point, something happened, or at this point, again, one particular point on this EPH diagram will tell you two coordinates. Let's say I pick this point. I pick this point. So this point will tell you what is the environment that contribute to this reaction. So you have two. One is y-axis data, will tell you the potential voltage that can measure, and the pH that appeared in that particular point. Again, potential here is because of the corrosion process, and it is not an external supply of electricity. Again, corrosion and electrolysis is different. Corrosion happens without external electricity. So the voltage or any electricity properties that you measure here, it generates on the surface itself through the exchange of electron, okay, that we covered previously. Okay, so just take note on this. Don't mix up with the electrolysis process. Okay. Right. So basically, this diagram you can check thermodynamic stabilities. Okay, and from the data here, you actually can derive the species or the products of the corrosion process. Again, this is an oversimplified graph. This is oversimplified graph. It just tells you what is the axis, what is the y-axis, what is the x-axis, and what is happened in between. Okay. So in later slides, you will see more information on here. But before we go deep into the diagram, we can see the mode, we can see the environment on this EPH diagram. Okay, something like that. So this is a more detailed graph, and this one again is not yet. There's lots of pattern. There's lots of line pattern on the EPH diagram. So this is one of the sample only. This is one of the simplest scenario that we can have. Okay, so on the left hand side you see the voltage, and the unit is voltage versus SHE is the measurement for corrosion. Okay, it's a measurement of different potential, because you know that in corrosion you have an anode, you have a cathode, right? You have anodic process and cathodic process. So these two will give you the different voltage potential between 2 points, right? So you can measure that one using special equipment, and the pH is more direct lah. pH, you can use pH paper or pH sensor to check the corrosion status. Okay, so as you can see here, you have line A and line B. Line A and line B, and again this one is for water. Okay, this one is for water on the ion. Okay, different material have different lines pattern, but this is what you see on the screen here is the simplified or you call a controlled sample, where you put water on the steel, pure steel, and then you can get this perfect line. Okay. What is all this line about? Okay, I slowly introduce you. So on EPH diagram, you need to ask yourself, what is this graph for? What is the element that you're talking about? It can be ion, it can be aluminium, it can be copper, or any alloy. Okay, plus water, oxygen, and hydrogen. Right? We have been seeing this element, water, oxygen, and hydrogen, in corrosion equation. Right? So this graph will tell you what happened to water, what happened to oxygen, what happened to hydrogen, together with the metal element. Okay. Now the first line on the graph, line A, will tell you the reaction of hydrogen. Okay, this line A, this straight line, will tell you the reaction of hydrogen, where hydrogen break into ion, positive charge and negative charge. Okay, so this is what happened in line A, and it's an equilibrium line. So meaning, what I mean by equilibrium means along this line, the charge is stable. Means again, this is a measured. You can measure experiment. in the experiment, right? So you can detect all these points and then you can plot the graph. You can use instrument to auto plot the line for you. Okay. Okay. Second line, which is a line for the process of water. Water break into ion charges, positive charge, negative charge with water. Means you, A is about hydrogen, B is about water, how water break into charges. Okay. So as you can see here, there are some notation here. So what happened at this section? What happened at this section, which is below the line? There's a double dash there. It indicates that there is the thermodynamic driving force for this process. Okay, meaning below these charges, right? Below this line, this process, it will be will happen, right? This process will happen, and as you can see here, below this line, the water is stable, but with a one remark there. So what does this remark? It means below this line, as you go below this line, there's an increasingly thermodynamic driving force for oxygen reduction. Okay. For your catalytic oxygen reduction. One is hydrogen evolution, right? Evolution, and another one is oxygen reduction. So this zone above this zone is oxygen evolution and acidation. This one is below, this zone is hydrogen evolution and alkalization. So what does this all information means? Means that if the point that you test, the environment that you have, it will trigger different reaction. Okay, let's say you are given one value of your potential, you're given one value of your pH, the environment setting, you have a pinpoint location, either you fall into this region, or this region. So if your point is, let's say I pick this X-strict point, so if your point is stay within this region, your water is stable, and however, this region onwards, this region, you can say this region, you are having oxygen reduction process. Okay? And below this point, you are having hydrogen evolution process. These are the fundamental information that you have. I try to give you a more specific example later on, maybe next class, on how to, I give you a scenario, maybe I give you an element, and then you try to construct this one. At least you have an idea what is this, right? So for today, we just introduce you what are the components that we expect on the potential pH diagram. Okay, so you have two lines, line A and B. Each one of you tell you different process. Okay. Now this is one of another example. Okay, again, this is only show you the axis, the A and B line. This one is more near to real scenario that you have, but of course, from experiment you only have all the graph here, and this line and this line you can check from the handbook. Means you can, or on the machine itself already calibrated for line A and B, and then you put in the sample and the machine can plot the graph for you. Okay, now for this graph, you already put in the corrosion behavior on the graph. Okay, and again we are seeing potential pH diagram. This one is for ion and water, right? So we will see the thermodynamic boundaries on the EPH diagram. Okay, and different corrosion can happen if you've given the environment value. Again, environment value consists of potential and pH value. All right, so you can see different kind of corrosion on this chart. Okay, for example, right? If your environment value happen, you will have pitting corrosion. If you have value on this side and below, and on the left hand side and below this line, above this line, then you will have uniform corrosion happen in this region, and so on. So you have a mild pitting and severe pitting, means very serious corrosion here. Right, mild pitting is here. Okay. So actually you can guess lah, right? So by looking at the pH value, previously in a common sense, you know that when you have more acidic, the corrosion will be activated, and the process will become faster and faster. So as you read the pH value, let's say this point you project down is alkaline, right? It's more than 7, right? So the corrosion will still happen, but in a slow manner. However, if you reduce the pH value, maybe 6, you project up. So over here, you will see same process happen, but this point, because of more acidic environment, we have more serious corrosion happen. And on this chart, I give you, for this particular setting, you will see more serious pitting corrosion happen, right? Okay, so this one you can read. Okay. Now, what does the application of EPH diagram or potential pH diagram in, let's say you graduated, you already finished your study and you go into work. So how does today's lecture will help you? Okay, so I give you 2 examples. One of it is marine boiler, or anything deal with temperature and metals, and you need to do some prevention steps, right? But before prevention, you have to know the reason why corrosion can take place, right? So marine boiler, I give you a cut away diagram so that you know what is boiler. Marine boiler means on the ship itself, how the crew can get hot water because it's generated from boiler, and also how you generate steam for ship operation, all right? Or maybe in the submarine that old submarine that need boiler to maintain the temperature of the submarine, especially you submerge underwater. Right, the temperature outside is very, very cold. You need to maintain the warm temperature inside there. So, and for the operation of the ship or the submarine. So this is the cutaway. So basically, what does the marine boiler do? Is that you generate heat or flame, and then you have a loss of tube. You loss of tube, and within this chamber, you have water. Okay, you have water, and the water will submerge the horizontal pipe. And what go through the horizontal pipe? It can be just normal water, or it can be chemical, it can be air or some or some chemicals, right, to do the heat exchange over here. So it might be cold water, it might be chemical that go inside the horizontal pipe and exchange the heat energy with within this chamber. Okay. All right. So I think I have one video for you just to illustrate what is marine boiler operation. And this one is a old design. It's an oldie, but you can get the idea. Okay.
This fascinating document is a boiler plan, something that goes right to the very heart of maritime history. Boiler plans like this were created to allow the safety of a vessel to be certified by Lloyd's Register. Today, more than 8,500 plans like this survive in their archives, a wonderful collection. But what do all of these lines and shapes actually mean? Why are they so important? The boiler created the steam that was required to make a steam engine work. This particular boiler is a double-ended Scotch-type boiler fired by liquid or solid fuel from both ends. We start in the middle of the boiler and see how the centre section, the combustion space, is supported. The two large holes are for the furnace tubes. The smaller holes for the fire tubes. The furnaces are corrugated to give added strength and to increase the area available for heat transfer from the hot gases in the furnace to the water. The outer tube plates are put in place, linked by stay rods and secured by nuts. The fire tubes are now inserted, rolled into place with a tube expander. There was no welding until well into the 20th century. The boiler shell is then riveted in place and a steam valve located on top to distribute steam. The boiler is now filled with water. Note that the crown of the combustion space and all the tubes must be covered by water to prevent overheating and potentially catastrophic failure. The furnaces are then lit from both ends of the boiler. Hot gases pass through the furnaces into the centre, up through the fire tubes and then out to the exhaust. These fire tubes heat the water that creates the steam, which is collected at the top of the boiler and then distributed via the valve.
So basically this operation of a marine boiler. So what does this marine boiler so concerned in corrosion? Now we know that corrosion process when you use metal or alloy, when there's a water, when there's oxygen, when there's a hydrogen, then corrosion will happen. So you know that boiler, you submerge in the water, inside you have water, then corrosion will happen. Okay, so this is basically how you use the boiler to move the turbine and the ship operation. All right. The main concern here is because we are using steel and alloy material for the construction of boiler. So we need to take extra care, especially when it comes to corrosion. So I show you one accident of a boiler. So the size can be this big. Right? Let's see how what accident can happen. So explosion happened. So 10-meter hole on the site itself. Of course, this one is not on the ship lah. This one is boiler in the factory. So imagine what happened in this one happened on the ship. So it will be very serious. Okay. So that's why when we study about corrosion, we need to be careful, especially on the structure that deal with corrosion. So there are two factors that contribute to the activity of corrosion. Again, just now we introduced you the potential pH diagram. So of course, it will relate to your pH value and oxygen content of the water. Okay, there are two factors that contribute to the water-based corrosion. Right, water-based corrosion is the pH and oxygen content. Okay. Okay, now we are now in the aqueous corrosion. So if you have a water-based corrosion, then pH and oxygen content will be very critical. And oxygen content have a strong influence. This is just a side note on the corrosion potential. Okay, so that's why on the potential pH diagram, on the y-axis of this diagram, most of the time are influenced by oxygen. Okay, so just take note. Okay, what can influence the y-axis is because of the oxygen level. Okay. Yeah. This is just to illustrate, just to expand the point. Some thermodynamic terms or some chemical terms, aeration. Aeration means oxygen level. Okay. Means more the higher content of oxygen means you contribute higher y-axis value. The y-axis value on this diagram is your potential. Okay. And then because of boiler, you are having in a high temperature, then it further contribute to the failure of the structure and the corrosion activity also, right? Because you're having a high temperature of the boiler, the structure will change profile, a change property, plus the effect of corrosion. And just a side note, because when you activate the boiler, the temperature of the boiler increase drastically. And then when you cool down, when you shut down the boiler, you also cannot straight away shut down. There will be a specialized engineer stationed for that specific boiler to monitor the rate of increase of temperature and also the rate of the dropping of the temperature. Because you know that metal, when it increase very fast and drop very fast to low temperature, the metal will change phases. And as you learn in material, metal will become brittle if you have a very drastic drop of temperature, right? So be careful when you go to work later, especially you come across a boiler operation. So what are the treatment? How do you treat corrosion that have two problems? One is the pH value, one is the oxygen content. Okay, how do you solve or control these two elements? You know that corrosion happen in the acidic environment. So how to prevent it? We increase the pH value. So for marine boiler, normally the pH value will be around 11. ideally will be about 11. But the concept is you have to stay in alkaline zone. Okay? If can, this one at room temperature. And what is the consequences if your pH drop until is acidic level? As you can review from the previous lecture that when we mentioned about acidic effect, right? And you have to understand, if you do not do anything and the ship is running normally on the water, on the sea operation, where does this acidic come from? Okay, the first one is because of the sea salt, the contamination. You open your window, all right? You open the ship door and all this. So the sea water, sea and also the sea element, especially the salt, will go into the boiler room. Okay. Sometimes you clean the chamber, you clean the machine equipment, you use cleaning agent. So if you are not careful and you use the wrong cleaning agent, the acidic cleaning agent will stay at that particular spot and it will trigger corrosion at that particular spot. Okay, so one is seawater or sea salt. And that one is because of your cleaning process. You use cleaning agent that do not clean properly. There's a residue still inside the boiler. Then you will trigger the acidic environment. Okay, so these are the two high possibility for marine boiler. And this is the diagram that we will have for marine boiler. Okay. So I think we have a short break before we go deep into this diagram. Okay, let me stop the recording.